Okay, so for my video, I chose to do number 77 from 9.2, which is called Computing with Power Series. The problem starts off with giving us a function and a series, and also a interval to look at it on. Part A says Sn of x is the sum of the first n terms of this series, and it gives us n equals 5 and n equals 10. It then gives us the sample points x equals negative 0.9 all the way to 0.9, and asks us where is the difference in the graphs the greatest. So the next thing I can do from what they've given us is take the values of n in the functions and put them into Desmos. So here I have the graph of the function, and here is the series, and now I'm going to input the values for n that they gave us. So those values were 5 and 10, so first I'm going to do 5, and I'm going to look at the graph, and it very clearly shows that at the endpoints, which were negative 9 and 0.9, so here's 0.9 up here, and negative 0.9 over here, the difference is the greatest. So it's the difference is the greatest at the endpoints for n equals 5. So the next thing I'm going to do is do n equals 10. And sorry I'm not using Screencast-O-Matic, but here we can look at the graph, and both lines clearly have the greatest difference at the endpoints again. You can see at negative 0.9 and up at 0.9. If I scroll all the way up, the difference is increasing, so at the endpoint it would be the greatest. So from the graphs we can tell that for both graphs the difference is greatest at the endpoints, which were negative 0.9 and 0.9. So next, looking at part B, it says what value of n is needed to guarantee that the absolute value of f of x minus Sn of x is less than 0.01 at all of the sample points. So since the difference for the sample points is greatest at x equals 0.9, we know that we can put it into the function and find that f of 0.9 is equal to 100. So using this, we know that Sn of x must be between 0.01 and 100. So I took these facts and put them into this equation. 100 minus, and this is what I determined would have to be the value that we need to get less than 0.01. So it has to be 99.99 and then something after that. It has to be bigger than 99.99 to be less than 0.01. So thinking about this for a little while, I went back to Desmos and I opened up a new tab and thought about the function and how it relates to the series. So Sn of x, if we put in 0.9 for x and we put in values of n, it gives us a number value. So I'm using Desmos kind of as a calculator here, but it works in the end. So thinking about this value, I first started at 100 because I thought, okay, well, the function equals 100 when 0.9 is subbed in for x. So I looked at that and it's 99.9707 and so on. So we're actually pretty close. And then obviously if I put in less, then it gets smaller, so we know we need to go up. So I put in 110, and let's see where that gets us. And that gets us really close. That gets us to 99.988. So let's just go up another one. 111 gets us to 99.899, and 112 gets us to 99.9908. So this is the smallest value of n that gives us less than 0.01. Using what we learned from the graph, I said that S112 of x is needed to guarantee that the absolute value of f of x minus Sn of x is less than 0.01 for the interval of -0.9 to 0.9.